Teepen here. So, on November 30th in 1954, in Oak Grove, Alabama, a meteor lit up the sky. Now, this meteor is a very special meteor. I mean, while it did happen over 50 years ago, it is the only meteor to have struck a human.
The Sylacauga meteorite came in on the sunward side of Earth. It was about the size of a grapefruit by the time it struck Anne Elizabeth Hodge, who only suffered minor injuries.
Now, thankfully, Hodges didn't get hurt. However, one could say that that meteorite had quite a bit of kinetic energy. Now, that energy must have come from somewhere. We call that potential energy. So, potential energy is the energy stored by an object relative to some zero position. Let me show you what I mean.
Let's say I drop two balls from the same level. As you see, they return to the same height. However, the ball on the left has a greater potential energy because its 0 point is greater distance than the ball on the right.
Similar to how we can demonstrate potential energy with gravity, we can do the same with charges. Here I have a positive charge, and here I have a negative charge. Now, we know that the opposite charges are going to create a force that attract each other. So let's just say that here at the positive charge, we make that our 0 point. As I pull the negative charge away, it gains some potential energy. Now, if I were to release this negative charge, it would gain kinetic energy and crash right into the positive charge because opposites attract. So the amount of potential energy that a charge has is dependent upon how far away it is from the other charge. For example, say I take this negative charge and I pull it here. It has a certain amount of potential energy. Now let's say I pulled it way out here. It would have even more potential energy, to where if I let go of it, it'll gain much more kinetic energy as it hits the positive charge.
Now let's take our ball of charge and stretch it into a line.
Now with the line of charge here, it becomes a little more difficult to calculate the potential energy. For example, if I hold a charge here, it feels a force evenly distributed across the line. However, if I move it over here, let's say, it feels more of a force pulling from this side than it is from this side. And while it is the same height as this one, the potentials are different because the forces are different. Now, while the shape of an object may make things more difficult, say like a disc or a donut, when you get down to it, the potential of an object only depends on two things: its charge and its distance.
Let's introduce the new concept of lines of equal potential. If you look at this grassy hill that I pulled off of Google Images, you know that there is more potential energy at the top of the hill and less potential energy at the bottom of the hill. As a result, there is a line along the hill where the potential energy is equal. These lines of equal potential energy are called equipotentials. Similar to the contours of a hill, we can draw equipotentials for a charge. We see that for a spherical charge, lines of equipotential form circles around the charge. And for a line of charge, it forms almost like a pill shape. Needless to say, lines of equipotential are always perpendicular to the electric field radiating from the charge.
So why do we care about these lines of equal potential? Well, what about using them to potentially power the world? In 1891, a scientist by the name of Nikola Tesla invented a device now known as the Tesla coil. The Tesla coil has the ability to produce power with no connection. In other words, it's like a wireless power. However, the strength of the power depends on how far you are away from the device. Similar to Wi-Fi, there are lines of potential where the farther you are away, the less power you receive. My name is Teepen, and feel free to check me out on Facebook or subscribe to my channel. Peace out.